was hearing whatever the discussion going on, when I was sitting there. So it is like this informal kind of way of discussing, and it was very nice. And I really like the environment here, and would like to come back here later. I mean, I will be coming back in September again. Okay, Okay, so I was just wanted to say that where Calcutta is. So this is India, and this is in the eastern part of India, but it's called West Bengal. Okay, and that is because Bangladesh was also part of Bengal at some point, and when it separates, this becomes East Bengal, and this becomes west of Bangladesh. It's called West Bengal. Okay, so I'm here. And my native town is somewhere here. India is a big country. We have this. So I wanted to just say that the distance and things like that. So, but then Google gave me a walking path from advanced studies to ISA Kolkata. Apparently, in 2,000 hours, only 2,000 hours, and unfortunately, you have to go through Ukraine and Iran. And if you like Afghanistan, India, and Pakistan, and okay, so basically, so you go through all trouble zones if you work. So what I want to, okay. So what I will start with a summary of my talk. And before that, I just wanted to know, I mean, most people are here from from physics or mathematics or economics. And so probably everybody has a mathematical background. That's what I'm assuming here. So so what I try to convince you during this talk is that first thing is that phase separation. If you do not know, I will introduce it to some extent. Phase separation as a transition is associated with a percolation transition. And this is true in 2 dimensions, always true. Whenever there is a phase separation transition, beside that, there is also percolation transition happening simultaneously. Same critical point. Okay, so 2 different transitions happening simultaneously. Phase separation transition, like a magnetic transition or a phase separation transition, has a different set of critical exponent, different universality. The other one is different. And I'll show you that. These are old words. Second thing I want to say is that if you look at a critical phenomena, the critical phenomena is generally governed by some set of relevant operators, which means that you have a fixed point, and that fixed point determines what is the behavior of the macroscopic behavior of the system. For example, for Ising model, right? I mean, when you're talking of phase transition or phase separation transition at criticality in Ising model, you are only talking about something called a Z2 symmetry breaking. Right? I mean, Z2 symmetry breaking in 2 dimensions. So Z2 is a group, and that symmetry spontaneously broken, and that's what you are talking about. So generally, it's a relevant operator, but sometimes in very fortunate or unfortunate situations, you might have a marginal operator in the theory. Okay. So then, if you have relevant operators, they grow, and you have to keep them. Irrelevant, you have to throw out. And irrelevant operators makes the basin of what you call universality. But if they are marginal operator, for every value of the marginal operator, you have a fixed point. Because it's not growing, it is not simple. So you have a line of critical points. Right? And because marginal operator remains in the theory, and if it is perfectly marginal, then you will have a continuous, line of criticality. And along the line, the critical exponents may vary. But then when the critical exponent vary, the original critical point, like, which is governed by the operator, that is one part of it. So the question is that if you see only exponents changing, you should not be deciding that you have a new universality class. This is not, because that would be marginal operator which is doing it. So in such situations, I will tell you how exactly to identify whether there is a marginal operator. Okay? So scaling functions in that case remain invariant, even if the critical exponents change. And I will show you that. Third one, I wanted to try, I don't know how long I will talk here, but then I will also talk, there is something called a motility-induced phase separation, which happens in active systems. And this transition belongs to Ising what I call super universality case. I mean, Ising universality with continuously varying exponents. Okay, which means there is a marginal operator. I'm not as good yet out to identify what is the marginal operator yet. Maybe some of you might identify. Okay, so what the phase diagram, what the picture here shows is a general idea that you have a particles and particles have certain interactions. And of course, if a given system, phase separation occurs when particle density is fixed. If you have a, if you allow the system to violation of particle density, then the phase separation transition becomes something else. Okay, so so basically you have a density and you have activity and you have interaction. Interaction goes this way, activity this way. So large activity here. So this dome actually tells you it separates because it's now 3-dimensional. In 3-dimensional, you should have a closed surface which separates one side to the other. And that surface is this surface. And inside it is phase separated, outside it is mixed. Okay. And for every value of j, you have a coexistence line, which means that if you have inside, the inside densities are not stable. The system will break up into some densities in both sides. That's what will happen. Okay. So, and this dome has a peak here, and that is where the critical points lie. Okay. What I'm talking of, the phase transition or the critical behavior, the criticality lies only on this line. And I mostly talk about the critical behavior here. Here, there is no criticality. I mean, the system do not have stable density. Okay. Is it clear so far? Yes. So let us see that one example, at least numerical example. I actually take away all the physical examples here. I thought that maybe people are more interested in mathematics. I don't know. Because I mean, I work on many different things. To an extent, I also work on studying spinal injury of patients in the hospitals, directly taking the spinal fluid and looking at their protein concentrations. And so all kinds of things I do. And also I do experiments on active matters. But then today I will not concentrate on that. Okay. So what, okay. Yes. So I just wanted to say that this is a numerical simulation of some 256 by 256 lattice. There are particles. And particles, here that is particles do not have no interactions. Particles are not interacting. It's only hardcore interaction. That just two particles cannot occupy the same space. That is the only interaction. And particles are 4 types. There is no interactions. Particles are only 4 types. And particles, the 4 types are called, they're named as east, west, north, and south. So some guy just wants to move north more often. Some wants to move south more often, only locally. Okay. And that's all. Okay. And then it turns out that even without interaction, the system actually makes some kind of clusters. Okay. And the simulations is very long. It's like 10 to the power 8 Monte Carlo steps. And you see that the system is showing phase separation. What is the meaning of phase separation here? That you could see that there are clusters which are formed, which are very, very strong clusters, like with some density, which are very high density zone, and which is coexisting with a low density zone. It's like ice water. Like if you are exactly at 0 temperature, and if you put water into the refrigerator, you would never know whether you find ice or water, because some part will be ice, and how much will be ice is not clear because anything can be ice, or whole thing can be ice. So there are 2 different densities. Okay, they coexist. So similarly here, there are 2 different densities coexist. Okay, and they're not going away, but the clusters make changing its shape. And towards the end, you could see that things are doing very fast. So this time is logarithmic. So you are like, initially it is steps are 1, and then later on times are 100, and then, it's an exponential scale. The time is, time is flowing in an exponential scale. So you can think that things are, the snapshots are very fast later on. So that's the reason we could see the coarsening phenomenon, because coarsening is a power law phenomenon, which is fatal fat-tailed kind of behavior. Power laws are fat-tailed. So to see the behavior, you must, in time scale, you should jump a lot. Otherwise, you don't see anything. It looks like it's stable here. So that's the reason it goes up to 10 to the power 8 steps. So this is the behavior I want to show. And this is pretty, to me, when I get to know it, it was very surprising to me, because I always thought the interaction is minimum, you need interaction. Because I did not believe that this can happen, and that is the interesting thing for me. Why? Because let us make this argument, and we will see where this argument goes down. Okay. So the argument is, so the phase transition argument is just why it cannot happen is this. You say that, okay, it happens. You start with, okay, I believe, okay, start with something happens. So now what you have is that you start with a cluster, but things are already in clusters. What is the mechanism that it happens? It happens because something, let us just only take east and west, something is trying to move east, something is trying to move west, and they hit, and they just don't know what to do, they cannot settle. And the flip, if the flip is very fast, then it will quickly get out of it. But if flip is slow, then they will remain like that very long, and by the time they clear this, somewhere else there is a jump. And that could be the mechanism. But now, if you start with a state where everything is jumped, they're jumped because they're blocking each other. So which means that the clusters, the left of the cluster is like this, and right of the cluster should be like that. And that's the way they're blocking. I mean, if it is like that, then they should go away, right? So they're blocking like that, like this. So now after, what will happen at this stage, that if you wait very long, one of them at the sweet time will try to flip. And once it flips, because there is no interaction, nobody holds it, and all particles are here, there's a lot of space available, you just fly it. And if the space is infinity, it is not finite, but periodic boundary condition, it will go as long as it goes because it's active. Active means that it has a self-proportion thing. It's like a bacteria. There's nothing will stop it, it will go far away. And then in another one, at some sweet time will go, but by the time it is far away, so there is no way to make a cluster again. So if you start with a cluster, it appears that it will break down. How do we make it stable? That was my argument to start with. Okay, so I never believed that this phase transition happened. So most people do kind of do a hydrodynamic theory of it, particularly the initial hydrodynamic when people integrate, they do it in one dimension, and it also show an unstable state. Start with a stable state, become unstable. But that is something which can happen in mini-field theory when you are doing it work, right? Because noise is very important in 1D. So one of my work, which I will not present today, I proved that one dimension such a separation cannot happen. It's a mathematical proof, and I'm not going to present it today.
In your video, you do have periodic boundary conditions.
Yes.
Or not. It means that the reason we are seeing clusters is purely because of the periodic boundary conditions.
So there might be something else. The argument I give maybe break down for some other reason. Maybe there's a time scale which is involved, which the argument it doesn't capture. So because most people in the simulation see phase separated state in 2 dimensions.
So we have 4 different species, north, south, east, west. So I would expect that if you have this horizontal band at the end, that at the top of the horizontal band, I have all the south species trying to move south, and at the bottom of the band, I have all the north species trying to move north.
Yes.
Can I see this in your, do you have different color schemes for your different particles? Can I see this in your video that this type of structure exists? What happened to the east and west species if I had a horizontally oriented band?
Yes, it is. So question is that in the time scale, if I run the video again, you can see that it can form also vertically. Did not you see this?
But I meant that the final state in your simulation is a horizontal band.
Yes. So now in a MIPS, if you are asking a question, let us say there are only 2 different kind of directions, east and west. South and east for the time, let us drop it. So only east and west. Will they phase separate? Yes. You don't need north and south. So how they will phase separate. So now question is, in a phase separated cluster, do you see the right hand side is predominantly is only left movers? Yes, that happens. Okay, so that's a natural thing which happens, and but then they keep moving. Like if it is east and west is there, it is not like that. Sometimes it is so. Sometimes in a square, on a square lattice like L by L, you always have bands forming like that. Or band can form like that. But if you take a rectangular lattice, that is one method which people use to identify how the clusters will form. Can you tell me? Can you guess how the clusters will form if you have a rectangular lattice? Is it this way or that way? You understand the question?
If you have east and west, I would expect if you had vertical bands. Yeah.
So you have this. So one way to make it half the things has to be filled. So it can be filled like that, or it can also fill like that. Half of them fill. But you can see entropically, the entropy is only on the surface. You see. So if you this is the lesser surface area, because this other direction is periodic boundary condition, because this is if this L by 2L, this is 2L into 2L 4L, and this is L plus L just 2L. So it is entropically this one is preferable always.
Is it because it's faster to form that way, or what?
Yes, because when the correlation length, you build correlation length, it hits the shorter direction faster.
Yes, sure.
That's the okay. Yes. So now what I wanted to do is that along with this, when the phase separation happening, you can also see the clusters are actually touching the boundaries from this end to the other end. Like the clusters is big enough and that touching. So and this connectivity among particles, this is a phenomenon, it's a geometric phenomenon. Right? I mean from this end, that end is connected or not. It's a geometric phenomenon. And this geometric phenomenon is generally described by percolation. Okay. So whenever a cluster forms, because the cluster has to be large size and it's a percolation phenomenon also happening there. Apparently, I will show you more details. It's not just guess, so we should see it more details. So to study that, I start my talk with percolation. So let us see that what is percolation phenomena. So you take a 20 by 20 grid and you put 50 particles, let us say. And the question you ask, it's a simple one, there is no dynamics. You just randomly choose some 50 sites, occupy them, and you ask a question that from top to bottom, if you want to move anywhere, can you move? So you start here, and moving basically means that you have a neighbor, right? And only through neighbors you can move. So you can see that it stops here. It stops at the blue. But now if you put 100 particles, that you can here and here, but still you cannot go it further. In 150 particles, it come up to this. But the time you have 230 particles, you have a path from top to the bottom. And once you is 0.575 in this system.
There's no diagonal move.
No, it's not diagonal. You can only your neighbor. Neighbor is only nearest.
Sure.
Connection is through nearest neighbor only. So now what you do, then you ask a question. The question is, this means percolating. So no, because it's not, you cannot go. And here and onwards, once it is yes, after that it is yes. You know this because there is always a path and then after that it will be. So you want to minimum point here where it starts percolating. And this is very simple, like, just 2 pipelines of code if you want to do in numerics, but this problem, a lot of interesting things are known and some things are not all known also. So if you ask such a question, it will go from an answer no to yes at some particular point. And that's a critical point. Any yes to no question always ends up in a thermodynamic limit is a phase transition. So there is a phase transition here. But how do I know? How do I know that this is just a guess or it's just a transition? What I do is that I try to make a bigger system and see what happens. So I just take this, trust me that I just take this and try to put this same thing, but sometimes rotated also. You are allowed to rotate and join them. Okay. So in a bigger system, right now it is 40 by 40 and 50 times 4 particles, 200 particles. Right? So in a bigger system, what do you want to see? right? I mean, so you still want to go from top to bottom, but then whatever happened here, more or less similar thing happens here. So if it is not connected, it will not be connected. So here it is not connected, here it is not connected, here it is not connected, similar thing. But here, just because there are connections, if you put them, you will get a cluster which is bigger. The size of the largest cluster, which is this blue one, here remains same. This is just one, here it is one, here it is one, and here whatever it is the same, here it joins and it becomes bigger. So which means that the size of the cluster is proportional to the size of the system. So a finite fraction of the particles belong to the largest cluster. So which means that the largest cluster divided by volume, if you take the limit v goes to infinity, you should have a finite number in this side and a 0 this side, because it's finite. So it's a 0 to non-zero transition, and it's a very beautiful thing you can study. And I also find some students, so I just wanted to say that how to study such things, phase transitions and criticality. So what you do is that's your order parameter, size of the largest cluster. What is clusters? Any two things which is a neighbor, you connect them. And there will be many clusters, size is S1, S2, S3, find the maximum one, and that's your, and divide by L square in this case, that is your order parameter. And this, once you find order parameter of problem, if you identify order parameter, the rest is it's a mean of certain quantity, average of certain quantity. But a quantity has fluctuations. It's a distribution. So it has a distribution. So the distribution of S max, the mean of S max is 5, but there is a variance. So you just see how the variance, how does it variance here? So the mean goes to 0 from this side, and variance diverges here because it just sharply goes away. So the variance actually diverges there, and that gives you exponent. How does the mean goes to 0? That gives exponent called beta. So these are the things you calculate, and then your fourth moment also you calculate. There is a correlation length in the problem, which also goes to infinity. I mean, so when the system goes through this, it goes through correlation length. The length scale actually grows. And that is why the thing emergence comes about. Because emergence is a phenomenon where, like, if you have a diverging length scale somewhere, I mean, that's what I thought, that there is a diverging length scale coming somewhere. So it's not whatever happens, even socially, it's not only located in the neighborhood, it actually populates for a large fraction of the population, and that is the way something big can happen. Okay. So the mean and variance give you some critical exponent. And okay, but and where exactly this number happens? So I get it for this one. It is exact. I mean, exact means numerically whatever I saying, that is what I did. 575. But if you take it larger and do this, you find that the critical exponent is this. It's still not known. It's a simple problem, but this number is not known, and but known up to some whatever 10 decimal places. This will have calculated it that accurately. It's a beautiful paper by Jacobson. Okay. So now what I do is that, so now I ask, what are the other quantity you have? So your correlation length, if you have a finite size, finite system, and why I'm saying this, because this is the behavior this is the way I determine critical exponent. I just wanted to convince you that this is something which will give you very accurately critical exponent. So you have a correlation length which goes the distance from criticality to the power minus nu, and nu is positive, which means that at criticality it diverges. Okay, so but in a finite system, the length, so correlation basically means that you disturb somewhere and how far the system feels it. That's your correlation length. Okay? So in a finite system, the correlation length cannot be bigger than the system size itself. How can a length be bigger than the system itself? It cannot accommodate. So it will be cut. This length will be just L in any finite system. So which means that in a finite system, there cannot be a phase transition. So there is a L here. And so you can always write epsilon is L to the power minus 1 by nu in a finite system. Okay. So then order parameter goes as L to the power minus beta by nu, because it is epsilon to the power beta, L to the power minus beta by nu. That is what it is. So now S max will be L to the power D, because this comes S max is this dimension and times L to the power D. So times L to the power D here. Okay. So the largest cluster has a dimension which is not 2. L to the power 2 minus D by D, beta by D. And if beta's nu's are non-trivial numbers, this is D, which is not an integer. It's a factor. So which means that you have a cluster, and a cluster will have fractal properties. Okay. This is a method how to determine how to critical exponent. I don't want to do this unless people actually ask me to do this later. Okay, so in the population, there's a very accurate method. As I said that, if you look at this graph, you can see how well they collapse. Like, there are 5 curves and you don't see any of them here. With a proper critical exponent, you can figure it. This is a very simple phase transition. So you can, by the time the system size is, like 100, you can get it. So now, what is the meaning of universality? That you can study this problem, not only square lattice, you can do hexagonal lattice. Hexagonal lattice also, you get the same numbers, mu equal to 4 by 3, beta equal to 5 by 36. These are exact numbers which is known. Gamma is 43 by 18, and D is 91 by 48. So this is being known. Exactly. Okay. So this is in 2D. In 3 dimensions, those are different. So you have universal critical exponent, but you can take, instead of square lattice, you can take hexagonal lattice, you have the same numbers. Instead of that, you can also define on a square lattice, instead of defining in terms of 2 sides which are occupied, are connected, that's a cluster. Instead of that, you can, you take lattice points and you drop bonds. Right? On a square lattice of L by L, you have 2 L square bonds. Of 2 L square, you use some fraction like 20% to fill up, 30% to fill up, but you fill up bonds. Okay. Then you ask the question. Then there is a transition, and the exponent, sorry, the critical number of things bonds you to fill is half, which means that in a L by L system, if you put exactly L square bonds, they will start percolating. That number is exact. That is known, but for side percolation, it is known. It is different, and the exponent that is called a bond percolation and the side percolation, they are same. Percolations in 2 dimensions has this exponent. That's the meaning. Doesn't matter what lattice it is. Okay, so that is the universality thing which we talk about. So, but this is known in geometry because there is no dynamics here. When you take something, throw some particles and study properties, there is no dynamics. So this is a geometry phase transition. Okay. And the critical exponents, by the way, are not independent. It's not that, every time you study something, you get some critical exponent. It's not like that. So the critical exponents are also related by certain rules. Like, nu D in D dimension is 2 minus beta, 2 beta plus gamma. There are scaling relations between them. So in population, there are 2 independent exponents. Rates can be calculated. So these are coming from field theories. Okay. So now what I am saying is that this geometric phase transition can be thought as a dynamical phase transition. Let us see how. So now, when you throw particles, now let's say you want 20 by 20 system and you are putting 50 particles. First you put, it's a different cluster. Second time you put differently. And if you take all of them and you ask, what is the probability of each configuration? Any arbitrary configuration probability is same. Right? And 1 by C, that is the probability. 1 by choose n sides out of L square. That's the probability of every configuration. Now, you can also think dynamically. If you take this system and you say that you start the particle, next time, you just move some particles. You say that if there is a vacancy, it moves left, right, this, that. Right? So dynamics is that particles can go to right. It's only vector. If it is vector, particle can go to move to right, left, do. So after some moves, you say that take a configuration and find its cluster. So it becomes dynamic. And this problem is called exclusion process in 2 dimensions. So 2-dimensional exclusion process where the partition function has nothing interesting. Still has a populace, still has a phase transition. It's a good question to ask. I will not answer it. It's a good question to ask, how does it happen? Because we already know that critical points are properties, singularities, or zeros of the partition functions, right? I mean, if somewhere it's called Lian zeros. So if you have a part, right? I'm throwing some words, so please forgive me. So it's also it's also singular, right? Critical points are singular. So, but here the partition function has no singularity. So how does the transition happen in 2D exclusion process? But it does, as I show you. So now we do this. So this is a dynamical phenomena, and this is where the transition will occur. The density here is not observable. Density is an input parameter, external parameter, because it's a conserved quantity, like just moving particles. If you write 20 by 20, 50 particles, you just have 50 particles, then you keep moving. So it is a conserved quantity, and you get the same transitions. I mean, you don't have to list the proof. It's a dynamical phenomenon. Now you can ask, what if the particles interact? Now it's become dynamic. They will also form clusters. What is the kind of interactions you do? Lattice gas, Ising interaction. So now, if you study Ising models, Ising particles, like lattice gas, and particles keep moving, but there is an interaction between particles. Particles like to be close by. Right? I mean, if they are close by, their energy goes down. So the Hamiltonian of the system is minus U Ni Nj. If two particles in a neighbor, energy goes down by a amount U. That is one kind of interaction, favoring interactions. Right? Particles close by. So in this model, and the dynamics, you can say that particle move with Ising rates, like metropolis rates. So now question that will it have a population transition or no? Yes, it will. You know that when the particles make this phase separating state, that's the cluster which has happened. Will it happen at the same critical point? That is yes. Will it happen at same TC? What is TC here? TC is.
You're saying you will have at the same value of the density? Is that what you mean?
Same value of density? No, because density is not a parameter here. TC is a parameter here. So density. So because it's a phase separating state, it's an interacting system. It's a phase separating state, and the critical point is only on the top. So you change. So.
Oh, sorry. No, it's the dynamic. Okay, sorry.
Yeah. So what we do is that minus U summation over I Ni Nj. You just write Ni equal to 1 plus Si by 2. Si is plus minus 1. Then, if you just put it here, then one term is a constant. You don't care, and another term Si summation over Si, which is just a field. So and another term is SISJ. So this will be minus U summation over I SISJ. But because of these two, there is a 4 plus this Si here and Sj, they will add up. So this is minus U by 2 summation over I Si. Right? In Ising model, ordinary Ising model, there is a transition. Like, there is this phase transition happens at Tc equal to 2 by 1 plus 12 of 2 log. That's the place where the transition happens. Equal to 2.269. Okay, so that is where the transition happens in 2 dimensions. So now the U, corresponding U, has become 1/4. So the transition that Tc will also go down accordingly. Right? I mean, the transition is beta in Ising model, so this is a critical point. But the transition happens only when the field is 0. H is 0. This is the curve when H is 0. But if you have a small field, then there is no transition. Because if you put a magnetic field in the system, you are forcing the system to become up. Of course, it will become up. There is no surprise there. There is no symmetry. Okay. So what will happen is that if you put a field, then the curve looks like that. There is no singularity anywhere. This curve is a singularity point here. Not singularity, but whatever, think here. If you have a field, you don't have any singular point anywhere. Okay. So with a field, that cannot be a transition. That's a different transition happens. It's a first order transition from this side to that side. We will not talk about it. So this happens only, this critical point exists when h equal to 0. So the critical point of Ising model is Pc equal to this, what I write, and h equal to 0. But if you take this, you have a finite h. So it cannot be critical unless this term vanishes. And this term can vanish. You make u equal to 0, but then nothing is there. You can only make si equal to 0. When summation over si equal to 0, from this relation, summation over ni equal to half. So the critical point in phase separation transition, of course, in this kind of system, interacting system, is rho c equal to half and Pc equal to 2 by square root of, log of 1 plus square root of 2 by 4. Okay, so that's the critical point of this, and transition and exponents and everything remains same because once this is 0, this term is not there. We are only solving the Ising model with a different interaction strength. Okay. But what is the percolation critical exponent? So now you have options. Percolation is beta is 1 by 8 already there, or a parameter exponent, right? So now you have, is it okay with people right now? Or otherwise I can, yeah, okay. It's okay? Yeah. So the question is, if I want to do, what is the critical exponent? That's what we want to find. So you have option that beta, for example, the critical exponent or parameter exponent beta can be percolation exponent, which is 5 by 30, what do you call? 5 by 36. Or Ising exponent 1 by 8. What do you expect? Or do you get a new thing? It turns out that you get a new exponent there. For percolation, beta becomes 5 by 96. And new remains 1. Critical exponent remains 1. So the temperature, this is beta p is percolation at Ising critical point is 5 by 96, gamma p 91 by 48, new to remain same. So this is new universality class, different from Z2, different from Z2. Z2 means Ising class. Okay. So we name it for the time being is 2D percolation. 2D Ising percolation, Z2P. It's also different from 2D percolation, ordinary percolation. It's Z2 percolation. Okay. So you have interaction between particles, the critical exponent change, the percolation exponent change. Now, how do you, I think I don't put that. Yeah, no, so basically the general question is, you can put more generally, saying that, okay, I have a system where the correlation between particles is 1 by r to the power a. I don't know, you can create it. Now, I put 50 particles, but the correlation among them is 1 by r to the power a. I always put it like that. Now, question is that what do you get? You get a percolation behavior that will be interacting percolation because there is correlation in the problem. And if the correlation is only exponential correlation, then you won't care. It's only when power correlation, then you care because that can change the behavior, critical behavior. Okay? So when it is 1 by r to the power a, there's a very beautiful property. That requires some discussions. I don't want to go there now. But and this particular example is a specific point, b minus 2 by eta. That is the value. I mean, because Ising, in the lattice gas, there is a critical exponent eta. It's like, so the critical exponent is CR equal to SI plus R. These are vectors. Minus SI average, SI plus R average. So this one at 1 by r to the power d minus 2 plus eta. So this correlations has a specific value in the Ising model. It is 1/4. D is 2, this is 2, eta is 1/4. So A is 1/4 in Ising model. Okay. So the question can be generalized and we can study percolation generally. Okay. I think I am going slow and I started at 11.
We live in Paris, so
Yeah, okay. So I'll
20 more minutes, at least,
20
20.
20 minutes. Yeah, okay. So this is called percolation. So the percolation is a very different behavior. So now question is that what will happen to the fractal dimension? Because fractal dimension for Ising model, if you take Ising model, as I proved, that it has to be d minus beta by mu, 15 by 8. And I'll not ask this question. I think I'll just mention it. So actually, for here, it is not 15 by 8. It is actually 187 by 96. It's also known exactly. So this is the whole reason. So question is that what we learned here, why exactly at the same critical point you have two different exponents? That is because in Ising model, what except beta and mu, there is an additional exponent which is called scaling or the critical scaling behavior for the critical what you call fractal dimension of the critical clusters. That dimension is not related to beta and mu. That's a new exponent, and that exponent is changing everything. That only exponent is changing everything. Okay, and what exactly happens is that there is a w here, like not beta by. You can always write d minus beta by w, but there is an extra factor called w, and w turns out to be 5 by 12 in this case. That is also exact proof for that coming from, again, field theory and Potts class, Potts universe, Potts models. Because percolation is related to Potts models. I will just wanted to do one more thing, and then after that I'll go to this activity, motility-induced phase separation. So now what I want to do is that how universal it is with W equal to 12. What I do is that instead of one Ising model, I take two Ising models. So you have one layer and the second layer, and here also particles or spins interact some way called S. Here there are sigma, right? I mean, this is just copies, but also there's the interaction between them, and the interaction is just sigma tau I, sigma j tau j. That's your interaction. And it turns out, which I'm not going to prove, that this lambda, this interaction is a marginal interaction to all orders. It's perfectly marginal, which means when you change lambda, the critical exponent of the system will vary. And the variation is also known explicitly. Okay, lambda is here, you put whatever value you put, accordingly, the critical exponents vary. Okay, so now question that when the critical exponent vary, each point you can study the percolation transition. Is it that at each point you get 5 by 12 or you get different? W also vary. It turns out that W actually remains same, and that is the result which you have. One of the results, I will go fast. So this model is called Askin-Taylor model, and you have exact marginality there. And here we say that even the critical exponent vary, they remain same. But now, as I say, that marginality means that there is also a. So I try to figure out what happens then. Okay, so I just summarize what I taught so far, or what I speak so far, is that summary so far is you have an Ising model, you have a phase transition. The Ising model is related to lattice gas. It also has a phase transition. So this critical point, I mean this graph, which is M versus T, when M becomes rho, so the graph has other side, and this curve is this curve. So this critical point in terms of T comes here. So you have a critical point at same TC, rho is half. So rho is half if you go like hit this critical point. So you take half field system, and now look at clusters, and then you get Ising clusters. But calculating this, what is the critical density, is not something very easy in a system where you do not know what it is. Okay, so to an extent, that Binder, Carl Binder, he tried right now, has one method proposed in 2018 only. So now, at the same point, you have a percolation transition. When the phase separation transition happens, you have a percolation transition, and the percolation transition has a different critical behavior, but they're related. And the relation is exact, like 5 by 12 in this case. So instead, so the point is that instead of studying phase separation transition, many people study phase separation transition. If I ask very seriously, what exactly the order parameter for a phase separation transition? A good order parameter for a phase separation transition. It's hard. In IG model, you know magnetizer, but magnetizer here is fixed. What is the order parameter? So people take many different things, but one of the things which I'm saying is that take the order parameter as the largest cluster, and that works much better. So much better. Cleanly you get all exponents, and then you can study phase separation, all phase separation transition. It doesn't matter in a social system or economic system or whatever. So this is the better way to study critical behavior. So what do people generally do? What people do is that, like, as I say, that you take a system to get order parameter. This is Binder 2018. Is that you take a rectangular system of size 2L by 6L. Then you know that the clusters will form vertically like this in the shorter direction. And this particle is the center of mass. You put some blobs here, and whatever density you get here, that is your liquid density, high density phase. And this will have a boundary. So you have to leave some space. So this space is left, one L is left, and the distant part, like this and that, makes another one that will give you a low density phase. So the densities of these boxes will give you low density, and this will give high density, but it requires L by 6L. That is the method, and it's very hard. 30, he could do only 36. L is, right, L is 12. Okay, so it's very hard. Other method is to find, well, if you have two density coexist, if you find what is the density distribution, you should have double peak. Right? And wherever the double peak vanishes, you call that is my transition point. It's also hard. You cannot get very accurately, locating where exactly it happens. So I'm just saying that take this percolation as your order parameter, study it, you will get much better results in any study. That's my claim. And I try to show it next in active systems. Yes, I just take another 5-10 minutes and then 10 minutes, let us say. And before that, if you have questions so far, you can ask. So what I convinced so far in the first part of my talk is that percolation and phase separation happen simultaneously in 2 dimensions, not in 3 dimensions. Because there is also a reason for that. So for 2 dimensions, if you want to go from one side to the other, there is no, so for example, in 3 dimensions, a cluster can form like that. Right? You have something like this. Right? And they're not touching, but they're overlapping. In 2 dimensions, you cannot form something like that. Okay. So people actually, there are very beautiful works regarding this, but anyway, I stop and I wait for a minute. There are questions on this. Yeah, okay. So far good. So now I say motility induced phase separation. As I say, so what is this? So when you talk of particles, you think of some spherical particles because they can move both ways, any direction. So now let us say in a pool of spherical particles, you have one pegged spherical particle. That particle can go anywhere because it will be hit by other particle and the direction is arbitrary, it will go everywhere, it will just make a diffusion. But now let us say the particle is not sphere, the particle is just elongated. It's so difficult to imagine this. I'm actually doing such experiment. So now this particle, because there is an axial direction, it will displace less in perpendicular direction. Now it has to displace a lot, it has to move this way. It is easy to move like this. So this becomes a nematic particle. Right? I mean, because it will can go forward or backward. Now let us say that the particle is like a screw, which means that one side is thicker, one side is thinner. And that is actually holding in a system of spherical particles. Then it is very easy for the particle along the axis move one direction. Because it will displace very little. It will start moving like that if you start vibrating. Okay? And this motion that you have an axial direction, and a directed motion, preferably in one direction, along the axis, is observed in nature by many physical systems. Fish, because fish move only along their head, it never goes towards the tail. Like moves preferably like that. So that is the way bacteria, fish, or many other kind of biological things are modeled by active systems. And fish, for example, create the schools, fish schools. So now question is that is it only a statistical property or is it something else you need? Do you need interaction between them that the fish do see, or you do, if you have a collection, it will automatically make schooling. So it turns out that schooling, you don't need interaction, it automatically will happen. Just that they cannot occupy the same space is good enough. The direction already create clusters. That's the demand of active systems. And this kind of clustering is called motility-induced specificity. So to model this, I start with simple Ising model because I know this lattice gas. And all I do is that lattice gas, but the lattice gas particles in the lattice gas is directions now. I'll make them east, west, northeast. I will take the same Ising dynamics, but I will just put direction here. Saying that this is the same move, energy is same, but it will move, the one which is east can only move to east. Even if there are vacancies in the west, it will not go. And then east, west, south, north, they can also exchange among themselves with some rate. That's all. Question that what will happen to Ising transistors? Why I start here? Because I want to start slow. Because I didn't know active method. So if you start here, at least one limit I know what happens to the phase transistor. Can you tell me what limit?
No tumble?
No, that is true. But also, if W goes to infinity, the particles most of the time keep flipping. Right? It just flip here to there, to there, to there, to there. So before it can make a move, it will flip some 2000 times. So right, the first move and the next move and the previous move are not correlated at all. Like doesn't know what is direction, so it's just moving randomly. So W goes to infinity. This one will show a phase transitions exactly like Ising. It cannot, right? So now question is, I will go directly here. So temperature, because it's non-equilibrium problem, I will be hit by this question. So I will not use temperature. T is always 1. I just study the transition with respect to J, same transition. So what happens that when W equal to infinity, JC, we know what the transition, this is Ising on Sagar critical point. This is what the transition occurs, W equal to infinity. And then we ask a question, what will happen if you create activity, some small W, small activity you create? This is passive. And this W creates some activity. So what will happen to the transition? So now if motility helps the transition, then with activity, you will need lesser interaction. This is the curve. Right? I mean, because motility is helping, you phase separate. If motility hinders, then you get a curve like that. Right? And if motility is no effect, it's straight. That's all you expect. So what I find numerically is that the curve looks like this, which means it's rather the opposite. What I thought that motility is helping system to phase separate is not true. I had very hard time in publishing this. Okay, so it is not true. I mean, you cannot argue that the curve is up. I'm just putting the order parameter and trying to figure it out. There is no argument here. You can argue about the phase transition so that it is happening semi-universal, but there is nothing wrong with phase. The curve is up. So here, this is a situation where motility is not helping phase separation. It is hindering. The clusters, it's breaking. Because you see, at this point, right? I mean, if you have motility, at this point, you had a phase ordered state earlier. At this now it is disordered because of motility. This is disordered. This is disordered. So if at this stage, if you go straight, this should have been ordered. If no help, but you want more interaction. In presence of motility, you need more interaction. to phase separate. Later on, I mean, 2 years later, we now know why this happened. Probably this is not that motility is completely useless. In presence of interaction, it is this effect. It acts opposite. That has been proven now. So the interaction is the cause here. Okay, and then in all these systems, I try to figure out what happens to the transition. Okay, why exactly this happens? That, because many people have seen phase separation transition. So what went wrong in these systems? Like what happens? Is it some people, because in this paper comes these comments like, oh, lattice models, because we study only field theories, and lattice model is the whole problem, and then lattice should not be studied or something. I don't know, but then or is it a very slow coarsening so that you are not seeing it? Maybe if you wait very long, everything what I say disappear, and that is not true. I mean, every time I was very careful in making the statement that what is the steady state. First you go to steady, that's the whole point. Go to the steady state, don't leave the simulation in between. So problem with lattice models, and what else is needed? Or maybe in this one, something else you do so that the phase separation.
You understand intuitively why it's not helping?
Why motility is not?
Yeah, why is it making more difficult in the presence of that kind of interaction?
Paramagnetic interactions.
The ones that you considered, yeah. What is the intuition for? Because I mean, in the whole beginning of your thing is like, they get stuck, they form clusters.
So now,
okay, you don't have interactions.
So the argument,
clusters,
yes, very nice. So the argument against it is that what you need is that you make clusters, but you need a macroscopic clusters, right? If you don't have, in this problem, the one which is east is only moving to east. They will start, but they will start quickly. And they will never not come out very easily from that, because there is no other diffusion process which is happening.
Right.
Okay. So if there is question that you make clusters, but you also leave some rope, burn the house, but leave some rope, so that they can come out and can make some more, you have a cluster here, but everybody you want to join eventually. Otherwise how do you get a macroscopic clusters? So this is the one which is happening, that you create clusters very quickly, but you create only micro clusters. There is no way you can have a phase separated set which is a bigger cluster from somewhere. It will never happen. Because it will be here, it is here, and that's there. That is what. And so now question is very counterintuitively, if you now introduce diffusion into the problem, you will phase separate. Okay. So I drop the interaction here, only introduce back west. So the east, those which are supposed to move east, once a while can also go to other direction, east, south. Then this is little bit small. Then the phase separate. So the MIPS apparently is there, but you need this direction, and this has to be solved exactly with 2 particles, 3 particles. One can actually show that this is that. That create additional delta function in the problem if your d is 0. So that limit is very bad. So the lateral diffusion should be allowed. Otherwise, if you don't have lateral diffusion, you just stuck very quickly and stay there, more or less. And that is what I did. Now I don't have interactions, but particles which are east can also go to with rate p, which is lesser than 1, can go to other direction also. And this one gives you a phase separation transition here. That's the one which you're saying. This is clearly a phase separation transition, even at j equal to 0. Okay, and I study only the percolation. This order parameter, what you see here is percolation order parameter. And now the question is, whole point, at p equal to 0, you don't have a phase transition. If you take this model, p equal to 0, I show you that there is no phase transition just now. Right? Because if you look at this picture, when j equal to 0, and this is a disordered state for any omega. Right? I mean, j equal to 0, which is much lower than, this is 0.8 below. So it is a disordered state. J equal to 0 is a disordered state. So if there is no interactions, just having east-west particles will not phase separate. That's the demand. Now question is, for p equal to 1, now there is no interaction. Explicit interaction is not there. But now, I have this model because particle can, those which are supposed to go to east can go to other direction with rate p. Now, when p equal to 1, the direction has no meaning. These are just simple exclusion process. If p is 1, each particle is just moving left, right, nothing. So that also doesn't have a phase transition. So p equal to 0, you don't have a phase transition, separation. P equal to 1 also you don't. So if something happens, either nothing happens. If something happens, it has to be reaffirmed. Yes, that is what happens. So you can see that p equal to 0, there is no phase transition, and p equal to 1 also no phase transition, and you have a reentrant phase transitions. And I'm density half, so I'm seeing the critical behavior. So I study these points and try to figure out what is the critical behavior, and these are the critical points which I studied. All these points.
Your line stops before 1.
So this one we do, right? Yeah, much before 1. That must be special. We could not point out very clearly. We're far away from this, and we do not know where this point is yet very clearly. This is harder. Whether it exactly ends here or not, or it is just slowly below that exact only one p equal to 1. That question is a good, very good question, of course, but we don't know the answer. But all we know here that along this line, if you go, the exponents, critical exponents change continuously. I'll just show the critical exponent here. So you can see that this critical exponents like 1 by nu is changing continuously and very systematically as you go along the line. So apparently there is probably a marginal operator here, and in presence of marginal operator, so this is the part of this. In presence of marginal operator, what to look for? I think I will not go here. So there is this thing which you also figure out in presence of marginal operator. What carries the signature of the phase transition is this scaling function. Binder cumulent is a function of correlation length. Okay. So what is plotted here is that this p value, as I said, that for every p there is a transition. You look at this here. For every p there is a transition somewhere, and for all these points the critical exponents are different. Right? I mean, you can see the critical exponents are different. But for each of these points, you get this curve. This curve. And you don't have a fitting parameter. Just binder cumulent and correlation length, you want to make it dimensional divided by L. And you are plotting for all these points. And I have more points here. And I'm plotting them with simple Ising model, not even conservation, Z to universal class, Z to class. And that is the curve which is this black one. This is just simple Ising model. And I don't have a fitting parameter. So there are all these curves are the same curve. So the scaling function, the binder cumulent versus J is a function of J, not any external parameter. This function remains universal. This is to be proven. Numerically, many people have seen lattice. Yes, few people do. They also have seen it. Some papers has come up. But this is an observation which is true, not proven mathematically very accurately. The binder cumulent versus the correlation length carry the signature of the relevant operators, like the main fixed point, to which the marginal thing is passing. Okay. So one of them is the Ising model. So this one tells you that percolation, because I'm studying percolation property, percolation belongs to Ising universality class. And I call it Ising super universality class because exponent change and scaling function remains same. So I think, and then if you put interaction, this is what happens. This is this work in last year. So interaction makes these transitions. Like, J equal to 0, you still have this, J equal to 0, you have this line. But if you increase J, it goes down and it goes up. There is a reentrant with respect to J also. I think I will stop here. MIPS in Ising class. And so this is called run and tumble particles because these are only on a lattice and then go as long as they go in the east, and sometimes they tumble. These are unentangled particles, and there is no MIPS when j equal to 0 and p equal to 0 in this case. So positional diffusion is essential for MIPS. That's what we find, and we get a reentrant phase transitions. And MIPS actually belongs to Ising University. Another thing we learn is that if you want to study phase separating systems, study population, study the geometric property, and that's much better way of identifying whether there is a phase separating system, even in a continuous system. And I cannot, I should acknowledge my collaborator. So Indranil is a PhD student. He's now looking for a postdoc. He's already in India, ICTS. Abir is currently working third year. And all of them, these four students, like, they're master students, worked on that. I think, yeah, Kanti has 2 works, and these are all master students, and Sayantan is a postdoc. Okay, who's working in my group. And thank you for your attention. I think it was overloaded, so I did not know. I mean, I don't know whether it is too much of critical behavior. Yeah, okay.
Is there any question? No?
Yeah, okay.
In a case where RTPs can go any direction, right, does not have a space, there you do have these MIPS even without diffusion, right? Yes, but only repulsion.
Only repulsion,
Yeah.
and we can move in, it's a discrete one or continuous?
No, the continuous.
Yes, I have not studied it here, but okay, yeah, that will do.
Yeah. So, but now if you make the velocities not in 4 directions, but in 8, let's say, they can also move in diagonal directions.
Yes.
Do you expect then that you might have MIPS even without diffusion?
No.
No.
Yeah, no. Not possible. No, because I mean, all you do, why? Because, if you start looking at how particles move, it's only in the symmetry. So if the directions are symmetrical, if you create some very special kind of lattice that I do not know, maybe Kagome in 2 dimensions, then I'll be hard for me to talk about, because somewhere it is 3 directions and somewhere there is 6 or something. But otherwise, there is a symmetry, and if you try to coarse grain, you get the same coarse graining picture. Like, you don't have, like, the corresponding field theory will be the same. So if you have D equal to 0, the field theory, whatever you write, it will not depend on very specifically on the kind of lattice you use. That's the. So now you ask, yeah, I know what you're going probably. 8 it doesn't. Now you make it 16.
Yeah.
And then you make it continuous. How can it? But no, we should know this much, that continuous symmetries are different. So we have this theorem, right? I mean, so phase transitions in equilibrium, discrete symmetry can be broken in 2 dimensions. Ising can have a phase transition in 2 dimensions. X5 model cannot. There is no true long range order, right? So now, the limit of Q goes to infinity, or maybe whatever this calling the direction, this one goes to infinity is not the continuum one. As long as you are discrete, you're still discrete.
So it doesn't matter how many states.
No, it doesn't matter. Discrete symmetry. So the point is discrete. Yeah, maybe Z. So if you have Z K goes to infinity, does it become U1 or somewhere? No, right? No, I mean,
Promise anything.
okay, yeah, no. So I'm just saying that discrete is always discrete. So the theorem is that there is a Martin-Wigner theorem. So we just say that 2 dimension continuous symmetry cannot be broken. It's only discrete symmetry which can be broken. So Ising is the Ising ports, right?
I don't think it's U1, just.
No, it is not. Yeah, it is not. It cannot go. Yeah.
But memory magnet is for like
You-
equilibrium system.
Hmm.
Memory magnet is for equilibrium system. It works more.
No, this is the argument people use. But right, when you say that, MIP says the phase transitions happening in the continuous degrees of freedom. True, probably. But it is the responsibility of people to explain why it is happening in two dimensions. Just saying that it's a non-equilibrium system doesn't work much. We know that it is non-equilibrium, but how? Tell me, why is that invariant theorem doesn't work in non-equilibrium?
Well, because the derivation assumes the equilibrium. Right.
There,
The memory magnet derivation assumes equilibrium.
Marvin-Middle's theorem assumes equilibrium, but the theorem, when the theorem is said, 1D you cannot have phase transition. It doesn't tell you whether if it is not 1D, whether you can have or you cannot have. Marvin says only what it says. In equilibrium, you cannot have. It doesn't say non-equilibrium, you can have. It's not automatically implied.
I think what he's asking is that non-equilibrium, you can expect more transitions, right?
Yeah.
This is
Yes.
what he's saying. So,
Yes.
but your argument that you were making is in equilibrium. It
Yes.
sounded like.
Yes, that is the argument is equilibrium, but I'm just saying that, if it is not equilibrium, it especially has to be proved that if there is a phase transition. The theorem says the theorem itself, for example, 1D, right? There is a non-existence theorem. A phase transition cannot happen in 1D. But if you look at very carefully, the theorem is based on something called Perron-Flovenus theorem, which is just a property of a finite dimensional symmetric matrix. So you cannot have, for finite dimensional symmetric matrix, the largest eigenvalue cannot touch anything else. There is no crossing, eigenvalue crossing. That is the one which translates. For example, somehow you create matrices which which is not symmetric. Non-equilibrium makes it not symmetric transfer matrices possible. So then you can have. So you can have in 1D. So do you have one? Don't you have 1D phase transition in non-equilibrium? Yes, we have. But whatever the phase transition you have, I cannot use that Margin. No, I cannot use the statement that just because Margin-Wigner theorem doesn't work, I have a phase transition. It only says that it allows me to have a phase transition, but it doesn't prove that I have one. It doesn't disallow me. That's all. It just allows me that there, right? I mean, you say that, yeah, you understand the.
Yeah, sure. I thought maybe one quick question more. You think maybe it has to do not just with the discreteness of direction, but also with your translation?
Yeah, consistent.
Okay,
Yes.
okay,
Yes.
I see.
Yes, consistent. Yes.
Yeah,
So if you drop the translational degrees of freedom, then it will not happen.
I see.
If you drop translation, that's what I'm saying. But if you have translation, if you drop the translation degrees of freedom, it will not happen.
Okay, because if you drop it, then you're in the equilibrium state.
Yes.
Okay, so yeah. We can ask and we thank PK again.
Yeah. Okay.